The modern Unicode uses 16 bits. So with 8 bits, we can do 256 possible combinations. With 16 bits, we can have 65,536 possible combinations. So we have enough combinations to use almost any letter of any alphabet in the world that's worth putting onto a computer. So Unicode is based on ASCII. The last 8 bits would be just like ASCII, but then if we add more bits, we can go on and have bits over here that tell us, well, now the last 8 bits mean something completely different. But here in the Western world, we usually think of ASCII and Unicode as just simply an expanded ASCII with a whole bunch of extra zeros on it. So that's how we store the information. I'll keep thinking about ASCII and thinking 8 bits at a time because that's the way I grew up and that's the way we usually think of things. So that's how we encode the information, and then I told you how it's actually stored, how the bits are actually stored in memory, just basically a long list of bits. Okay, so that's how information is stored. So why do we need data structures? Well, of course, we use data structures every day. We use lists, we use books, we use scrolls. Whatever we do to organize our data is a data structure. So let's look at a common data structure and how we use it and how a similar data structure is used on computers. And what I'm going to do is bring my book back here. So this is a book, and this particular data structure is printed. We can think of each one of these letters of the alphabet as 1 byte of memory. Now, the amount of information we can put on one page is variable because we can make the letters of the alphabet bigger and smaller, but we will assume that, like a computer where that's not really something that happens, that there would be a certain number of bytes on each page. And so we can put a certain number of letters. Each byte can contain 1 letter of the alphabet per page. Each page can contain a given number of bytes. Just for argument's sake, let's say each page can hold 128 bytes. Well, this can actually hold quite a bit more, but that'll come into use a little later. Let's just assume that's 128 bytes, so we can have 128 letters on each page. And then we have this organized into chapters, and then the contents tells us where each chapter begins. So first chapter begins on page 3, next chapter begins on page 9, next chapter begins on page 17. Okay, this works very well for a book. But what if we need to make changes? Well, the editor can go in here and write things in here, and the writer can maybe make notes in the margins or whatever. But to eventually get that redone, we're going to have to reprint the entire book because we can't erase it and move things around. So the next edition, with new information, we can't simply stick it in. We have to start all over and rewrite the whole book. Everything gets reordered, and then we have a new book. So is there anything in computers that works the same? And the answer is yes, CD-ROMs. Because once you make a CD-ROM, excluding the CD writables and rewritables, we're going to assume that these are the factory-made pressed CD-ROMs. Once you make them, they're made. You can't change them. And they have a structure very similar to a book. They have a few bytes that are organized. The first part of it, I'll just show our bytes in a string here. So there's 650 megabytes, so about 700 megabytes of information on a CD-ROM these days. And the first few, there's going to be some structure just for the computer to use, but just for the data, the first few are going to be a table of contents. Each byte is a letter of the alphabet, so it takes a number of bytes for each entry to say this is the name of this chapter. And now in computers we call them files, not chapters, but we could have just as easily called them chapters, with just we use the mental thought of a filing cabinet rather than that of a book. So we could have called them chapters. And so we take a number of these bytes to give a name to the chapter, and then we can put numbers in these bytes too. After all, we can make a binary number that looks like a decimal number. Just an example, I'll just use 4 bits here. That's the number 0. That's the number 1. That's the number 2. That's the number 3, and so on. And we can represent numbers in binary and convert them to decimal for the human use. And so we can store numbers there too. So we would have a number of bytes to give the name of a chapter, and then some bytes to give the page number, if you will, or somewhere down in this list of sectors is the sector where that chapter starts. So this is, let's say that's just, I just used the word sector. These are blocks of data depending on the system, how big they are. On modern systems, a sector is 512 bytes. In older systems, they might have been 128 bytes. They're just blocks of data. So I might interchange the word sector and block. It's just a group. So anyway, a page is equivalent of a sector. So a block of memory, I said that each page would hold 128 bytes, let's say. Well, we'll call each page a sector or a block. I'll just use the word sector because I'll just gravitate to that word. So this will tell us, that number will tell us the starting sector, and that will be the first byte of that chapter, and there will be the words in the chapter. And then when we get to the end, there might be some kind of a code that says this is the end of the chapter, or there might not be. We reading a book, we just have to know. There'll be some code that tells how long that chapter is, so when the computer is reading that, knows when to stop. But anyway, we have a structure of a table of contents, and then chapter, chapter, chapter. The table of contents has a name and a pointer to the beginning of the chapter, and the chapter may or may not have an end mark, but we certainly have a way to find the start of each chapter on a CD. Now on a CD-ROM, it's going to have some way of telling us that this is the end. There might be an end marker, or there might be something. I don't actually know the CD file system very intimately, but there's going to be something in either the table of contents or something at the end to say, the table of contents will say this chapter is so many pages long, or it might get to the last page and say this is the end. I don't know which it uses, but it will use some kind of code like that. But that's the way a CD-ROM is organized. And so there is a data structure that we see every day. Table of contents and chapters, pretty much like a book. Now I don't know if this even has a name. I suppose I could look it up and find that there's a name for this type of file structure. Actually, a CDFS would certainly be a name for it, CD file system. But let's take a look at another way data is structured on disks that, well, now is as good a time as any to talk about it. And that is an early system called FAT, or File Allocation Table. And that, well, before I erase this, it was pretty much the same as the CD file system, but it's designed for magnetic disks, such as floppy disks or hard disks, where we can erase and rearrange the data. So let's take a look at the problem and see how the problem was solved with what's called the FAT system. FAT stands for File Allocation Table.